So hopefully you've already watched the video introducing the different types of equations for lines in 2 dimensions, because you're going to need to have that background in order to be able to solve the problems. And that's what this video is about, solving the problems that requires us to use these different types of equations. So I'm going to skip example 1 because you should be able to fill it out from the other video. Let's go to example 2. So we're given a line in y equals mx plus b form, slope y-intercept form, and we need to determine a direction vector for the line. I always find it super helpful to just draw a quick sketch. So if our line is 8 over 13x minus 2, that's going to look something like that. Right? It's going to cross at -2 and it's going to have a slope of somewhere around a half. Right? So it's going to look something like that. And if I want a direction vector for the line, what does that mean? Well, remember, a direction vector is like saying a vector that's in the direction of the line. Right? It doesn't really matter where it is. It could be there, it could be there. It also doesn't really matter how long it is, as long as it's in the direction of that line. So how can we figure that out just based on that equation? Well, look at the slope of the equation, 8 over 13. We know that means that this equation is going to have a rise of 8 and a run of 13. So if this is 8 and 13 as your rise and run, what's the direction vector that corresponds to that going to be? And be careful here, because rise over run is the y over the x, but a direction vector, if we want to sort of make this our direction vector here, that sort of follows that blue path, it's going to be the x components and then the y component. So the x component there will be 13. So I'm going to call this m as our direction vector. The x component is going to be 13. And the y component is going to be that rise, basically, which is 8. So there, it's actually always the reciprocal of the slope of the line. Also note, I don't have to use 13 over 8. I could use 13 over 8 times 2, so I could use 26 over 16. That would also be an acceptable direction vector, right? Or even negative 13 over negative 8. Okay, so now we're asked to find a normal vector to the line. And again, what does normal mean? Normal just means perpendicular to the line. So if I have this green line here that's perpendicular to the line, we want a vector in that direction. So how can we do that? Well, we can go back. There's actually a few ways to do this. We can go back to our grade 9 and 10 knowledge about perpendicular lines, and we can remember that the slope of a line that's perpendicular is the negative reciprocal. So if the slope of our line was 8 over 13, the slope of the perpendicular line, so the slope of this line, is going to be the negative reciprocal, so negative 13 over 8. And if that's the case, that's the slope of the normal, right? If we wanted to find the direction vector along that line, right? Remember, we have to switch the y and the x. We have to switch the y and the x. So it'll be 8 over negative 13, right? So I'm going to call that n is 8 and negative 13. Sorry, not 8 over negative 13. 8 and negative 13 are the two components of that vector. So even here, with the direction vector and the normal vector, notice how those are also negative reciprocals of each other. We just changed the sign of one of them and flip them around. There is another way to do this as well. If you remember from the other video, you can find the normal vector by finding the equation in Cartesian form. And if you remember what Cartesian form is, it's where we just isolate everything, put everything on one side, and set it to 0. So if I was to set this equation to 0, we should also be able to find a normal vector. So let's do that. I'm just going to throw that y on the other side. So it's going to give me 0 equals 8 over 13 x minus y minus 2. So that's essentially our vector, or our line, in Cartesian form. Now, I don't like that fraction at the beginning, so I can actually just multiply everything by 13 to clear that fraction. And if we do that, we're going to get 0 equals 8 x minus 13y, and then the 13 times negative 2 would be negative 26. A little squish there at the end. But remember what this tells us. This tells us So that's nicer because it's all whole numbers as well. That tells us that our normal vector should be the a and the b values, which are this value and this value. So 8 and negative 13, which if we look at our other vector that we came up with, it's exactly the same thing. That's just two ways to solve the same problem. And then it wants us to find the vector and parametric equations for this line. I didn't give you very much space to work here, but I think we can still fit it in. So remember, if we go back, I'm just going to skim back over here to the other page, the vector form of an equation right here is r, so we're going to call it r, equals a point on the line plus t times m, where m is our direction vector. So the question is, well, what we need to do is we need to find a point on the line, and we need to find the direction vector. Luckily, we already have the direction vector, so we can call our line r. We have the direction vector. We need a point, actually. So what's a point on this line that's very easy? Well, we can go back up to our equation, and we can find basically any point on the line by plugging in an x value, but probably the easiest one is the y-intercept, right? We know, I should have drawn this sketch a little bit bigger, but this point is going to be 0, negative 2. That's our y-intercept. So I can put that as our point on the line, and then from that point we're going to add t times our direction vector, 13 over 8. Sorry, not 13, I keep saying that, not 13 over 8, 13, 8. That's our, those are our components of our direction vector. So remember what this equation tells us. It basically tells us that r, so our direction, or our equation of our line is 0, 2, we start at this point 0, 2, and we add multiples of this direction vector, 13 over 8. So we can break this up into parametric equations. Actually, you know what? I'm going to change one thing here. Instead of calling this r, I'm going to do it the other way. I'm going to call this x and y, because that makes it a little bit easier to break it up into parametric equations. So I just wanted to separate the x and the y there. So for parametric equations of the line, we just look at the x components and the y components. And if we look at the x components at the top, it's just going to be 0 plus 13t. So essentially just 13t. And the y component is going to be negative 2 plus 8t. There we are. So there's our vector equation of our line and our parametric equations of our line. Alright. So here we have to find the slope, Cartesian and slope y-intercept forms of a line that's normal to 2, negative 5 and goes through point 4, 10. So whenever you're given a normal, the easiest type of equation to use is a Cartesian equation, because it's going to be ax plus by plus c equals 0, where a and b are just the components of your normal. So we know those are 2 and negative 5, so let's just plug those in. 2x plus, oh, now I'm going to change it to a minus because it's going to be subtracting 5 minus 5y. We don't know c yet, so I'm going to leave it as c equals 0. And in order to complete our equation, we need to find c, and hopefully you can see how to do that. We have this point 410, we can just plug that in. So 2 times 4 minus 5 times 10 plus c equals 0. And I can just solve that as 8 minus 50, and then, so negative 42, and bring it to the other side, so c equals 42. Okay, so our final equation will be 2x minus 5y plus 42 equals 0. That's our Cartesian equation. And then to turn this into slope y-intercept form is just y is explicit. Y is by itself. So we can just rearrange that equation. I'm going to stick everything on one side. Actually, I'm just going to do 2x plus 42 and then move that 5y to the other side. And then I have to divide everything by 5. So I'm going to end up with y equals 2 over 5x plus 42 over 5. And that is our slope y-intercept form. Okay, the next question wants us to find the vector form of a line passing through two points. 2, 4, which is going to be something like that. So I'm going to call that 2, 4, and negative 5, 8. Negative 5, 8. Oh, that's going to be all the way up here. Okay, so a line goes through these 2 points. Sorry about the crummy sketch, but it gets the job done. And we need to find the vector and parametric equations of this line. So how do you find the vector equation of a line? We need 2 things. We need a direction vector and a point. We already have a point on the line, so that's not a problem, but we need a direction vector. How can we find a direction vector? We should know this from the last unit. If we have 2 points, we can find a vector that goes between those 2 points. So I'm just going to do it in red here. Our direction vector m can be from that first point to that second point there. And we find that by essentially finding the difference in the x's and the difference in the y's. So I'm just going to do 2 minus negative 5, so 2 plus 5 basically, and then 4 minus 8. So our direction vector of our line is going to be 7 and negative 4. So there's our direction vector. We have a point, so we can write the equation of our line as xy equals, starting with the point. You don't have to start with the point. I'm just going to choose 2, 4 because it's easier. You could start with either point actually, plus t times our direction vector, 7, negative 4. And there is our our vector form of our line. And then parametric is very easy once we have this. We just look at the x components, which would be x equals 2 plus 7t, and then the y component, which is y equals 4 minus 4t. There we go. Not so bad. Example 5 is similar to one that we did on the previous page. I'd encourage you to try it yourself and pause here before watching me do it, just as a little test to see if you know what's going on. So to do this, we know it's going to be passing through 5, negative 2 and parallel to 2, 3. And this actually is a vector. This is a direction vector of 2, 3 there. It should have an arrow on top. Now remember what we said. How can you... So if it's parallel to 2, 3, the easiest way to approach a Cartesian equation is if we know the equation of the normal, right? Because then we just plug that in for a and b. Actually, I'm just going to write that out. ax plus by plus c equals 0. That's what we want in the end. We want to find what a, b, and c are. So if we know an equation of our normal, that's just going to be our a and our b values. Well, if the direction vector is 2, 3, because it's going to be parallel to that line, any parallel lines are going to have the same direction vector, right? So if that's the direction vector of our line that we're looking at, what's going to be the normal? And if you look at the pattern on the previous page that we saw, it's like taking the negative reciprocal. So we can flip these around, so it's going to be 3 and 2, and then we have to make one of them negative. It doesn't actually matter which one. If you think about it, negative 3, 2, and 2, negative 3 are just opposites of each other. So they go in opposite directions, but they are collinear. So it doesn't actually matter which one you make negative. So anyways, we can plug this in now. So a value, actually you know what, I'm going to change that. I'm going to make the b value negative, just because in our equation, you like to usually keep the a value positive, just to make our algebra a little bit easier. So I'm going to make this 3x plus, sorry, not plus, negative 2y plus c equals 0. And then same as the previous question, we can plug in that point to find out what c is, because we know it goes through 5, negative 2, right? So 3, 5 minus 2, negative 2 plus c equals 0. So that'd be 15 plus 4, so 19. Bring it to the other side, so c is going to equal negative 19. So our final equation, and it's a little squished over here, is going to be 3x minus 2y minus 19 equals 0. Okay? Now this is a great question. We have 2 lines. These are in vector form. Even though they look sideways, like the 2, 2 and the 1, negative 1, 3 are beside each other, that's just another way of writing vector form. This is actually the form that the textbook that you're using uses. But it's fine. It's the same thing. Just remember the first one is the x part and the second one is the y part, obviously. So we have 2 lines in vector form, and it asks us to find the acute angle the 2 lines intersect at. Okay, how are we going to do this? Again, I like to draw a quick sketch just to have some idea of what's going on. So my first line, I'll do this the blue line, goes through point 2, 2, and has a direction vector of -1, 3. So that means the x component is going to be -1. It's going to go to the left by 1 and down by 3. So that's going to take us somewhere down here. So I'm going to go like that. Careful that you're not plotting the slope. It's really easy to get mixed up, and you think the rise and the run, -1 and 3, but that will give you the wrong angle actually, or the wrong line. So careful not to do that. And then I'm going to draw this second line as at 3, 4. So 3, 4, I don't know, something up here. I don't know exactly where it is. It might be on that line. It might be beside that line. But that's fine. Oh, sorry, that's wrong. It should be at 5, 1 is our point. So 5, 1 is actually out here. Let me erase that other point. And then our direction vector is 3, 4. So the x component is 3 and the y component is 4. So it's going to be up here like that. So the line, I know it doesn't meet exactly through that point, but I want just a rough sketch of what's happening here. It's going to be something like that, I think. So if that's what we're trying to do, or if that's what's happening with those two lines, it wants us to find the angle between them, the acute angle between them. So I'm going to call that theta. So if theta is the angle between those lines, how are we going to find them? Think back to last unit. Is there a tool that we can have, that we can use to find maybe the angle between two vectors? Because remember, along the red line here, there's a unit vector, and along the blue line here, there's a direction vector, right? So if we can find the angle between those two vectors, we've essentially found the angle between the two lines. So the key is dot product. Dot product will let us find the angle between two vectors. So essentially we just need to dot -1, 3 and 3, 4, which are our two direction vectors. One thing actually, I'm going to draw some attention to something here. I forgot to do this earlier. Notice how in the first equation we have our parameter as s instead of t, and our second equation has t. When you have two separate equations on the same graph, it doesn't really make sense to give them both the same parameter, because s and t can be different things at the same time, right? You can be in different points on each line at the same time. So that's why we actually have to have two different parameters. So we usually use s and t for 2, and that's why I said where s and t are elements of real numbers. That generates the line. So anyways, going back to our question, sorry about that. If we find the dot product of those two, we know we can sort of use that to find the cosine, or sorry, find the angle between the vectors. So going back to our equation for dot product, it's going to be a dot b is equal to the magnitude of a, magnitude of b, cos theta, and we should be able to solve for that angle. So pause it here, I'm just going to show you the answer. I'm not going to go through all the algebra with you. You should be able to do that yourself. So if you do that, it ends up giving you theta as 55.3 degrees, which is the angle between those two vectors. Awesome. One thing, notice I just called the vectors m1, the direction vector of line 1, and m2 was the direction vector of line 2. So that's just an easy way to label them. Okay, the next question asks us to determine the point of intersection of these two lines. If we had these in y equals mx plus b, this would basically be a grade 10 problem, right? We could use substitution or elimination to do it. But we're given these lines in vector form. So do we have to convert both these? I mean, we could turn them both into parametric equations, then turn them both into symmetric equations, and then turn them into Cartesian equations, and then solve. That sounds like a lot of work. Is there a way we can do it a little bit simpler? And I'm going to actually start by writing out the parametric equations of each of these and see if anything comes to you. So for L1, the equation is going to be, the parametric equation is going to be x equals 2 minus 1s, or just 2 minus s, and y equals, 2 plus 3s. And then for line 2, the equation is going to be x, the parametric equation is going to be 5 plus 3t, just looking at the x components, and the y component is going to be 1 plus 4t. Is there anything we can do here to find the point of intersection? Well, this is the thing. we essentially have 4 equations here, and we have 4 unknowns, x, y, s, and t. So we should be able to solve this. And the way we can do it, notice how on the left side and the right side, equation 1 and 2 both have x's in their equation already. They're both isolated for x. So can't we just plug those into each other? If I plug x into x, I'm going to get 2 minus s equals 5 plus 3t. So that's one equation. And then can't you do the same thing for the y's, for the second value? So 2 plus 3s equals 1 plus 4t. So now I have 2 equations and 2 unknowns. I should be able to solve that. So pause it here. Try to solve this equation. Isolate for a variable. If you're not sure how to do it, isolate for a variable, plug it into the other one, and solve for s and t. Then see if you can find the point of intersection. Okay, pause it here and give it a shot yourself. So unfortunately I didn't really give you enough space, so I started to go to the next question. But all I did was I isolated for s in the first one, plugged it into the second equation, solved for t, and I got t is negative 8 over 13. How does this help us? Well, look back at our original parametric equations. If we know t is negative 8 over 13, can't we just plug that in to here and here to find our x and our y coordinates? That's exactly what we do. And I will let you do that yourself and find out what the x and the y coordinate is. Okay, let's just go on to the last question very quickly, example 7. Are the lines 6x minus 2y minus 3 equals 0 and negative 3x plus y plus 17 equals 0 parallel, perpendicular, or neither? Think about what each one of these equations gives us. They're in Cartesian form, so what does that tell us? Right away that tells us what the normal is. So the normal of our first equation, this should be sort of automatic after a certain amount of time. The normal of our first equation is going to be 6, negative 2. And the normal of our second equation is going to be negative 3, 1. Right? Just our a and our b values. So the question is this useful if we know that these are the direction vectors of the normal? Wouldn't it be more useful to have the direction vectors of the line? Well, it turns out something, this might be intuitive to you, but basically if the direction vectors of the line are the same, that means the direction vectors of the normal are also going to be the same, right? Think about it. If two lines are parallel to each other, right, the perpendiculars of those two lines are also going to be parallel to each other. So the question is, are these two direction vectors parallel, perpendicular, or neither? Well, just by looking at that, you should see a bit of a pattern. Can I go from one to the other by just multiplying it? And the answer is yes. How can I get from here to here? Or actually, even better, how could I get from here to here? What do I do? What about if I just multiply by negative 2? Does that work? It does. So essentially we can say that this vector here is a scalar multiple of this vector. So they're multiples of each other. And if vectors are multiples of each other, that means they are ... parallel, right? They're going to be parallel to each other because they're just multiples of each other. Same thing with slope, right? If you think of slope, you can have slopes that are multiples of each other. Those lines are going to be parallel or right on top of each other. So that's essentially the case here. Because they are multiples of each other, they are parallel. So, therefore, parallel. This is like really poor form here. I should actually say something like, because they are scalar multiples of each other, you can add that part in. Okay? How could we tell if they were perpendicular to each other? Think about it. Well, there's a few ways we can do it actually. We can see, first of all, if they're negative reciprocals of each other, right? That would tell us that the normals are perpendicular. Excuse me. And if the normals are perpendicular, that does mean that the lines will be perpendicular as well. The other way we can check, oh, and also it could be a multiple of the negative reciprocal. We'll talk more about that in class. But also, you could take the dot product of the normals. Because remember, how do we know if two lines are normal to each other or two vectors are perpendicular to each other? We take the dot product, and if it comes out to 0, that would mean they were perpendicular. If it comes out to anything else, it's going to be neither. If they're not multiples of each other and the dot product is not 0, then they're going to be not parallel or perpendicular.